All right, I will start off by saying welcome everyone. I see some familiar names, at least Joe and Nix. I think we're both in the last community office hours. This one is specifically oriented towards developers. I'm going to give kind of a brief overview of our formatting. So again, we will allow Eric, like the subject matter expert, to talk for about 40 minutes on 3 different topics, and then we'll allow the last 15, 20 minutes, kind of like an open forum if you have any questions about what he's been working on or any suggestions for the topics for next week. So this week, we're going to be going over 3 topics that Eric has chosen. The first one is the goals and reasons for Symmetry, why we decided to use Go, the journey so far, what we've learned along the way, and then if we have time, we're going to potentially show a demo here today. So one last thing before I pass it over to Eric, if you missed yesterday's meeting, every single week we're going to be having these, and we're going to be flipping the developer and validator calls. So while today is Wednesday, Eric is speaking today. Next week on Tuesday, Eric will be speaking in the morning. So Tuesday, MST 9 a.m., that's 15 UTC if you're not in Utah. And then Wednesday, MST 7 p.m., which is 1 UTC, is also another one. So that's this one. So without further ado, I'm going to pass this over to Eric so that way you can get us started on Symmetry.
Sounds good. So I'm going to share a screen here. I'll probably pop back and forth between some slides and then some websites. And like you say, if we have time, I'll show some code as well. So, oops, screen sharing needs to be on.
Okay, I got you. Go ahead and try.
Yep. Okay, that work?
Looks good.
Okay, so as mentioned, I'm Eric Lang, and you probably know what Pyrofex and Silvermint are, but if not, a couple links there. So I'm going to dive right into it. Why Symmetry? Well, if you do just a couple quick Googles, you'll find out that a bunch of money is lost through bugs. Notably, in the first half of 2022, $2 billion was stolen in the first half due to code exploits. And even more generally speaking, the cost of software bugs is huge. One estimate of $2 trillion in 2021. So bugs cost a lot of money. That's why we're doing it. It's especially bad for us on the blockchain because once you bake it in, it's really hard to get out. So we want to work super hard to make sure that the bugs don't get into the blockchain. So the goals for writing Symmetry was primarily for writing smart contracts and doing a good, secure job at it, but also, of course, integrated with the Silvermint itself. And a stretch goal for us that's very important is that it's general enough that it can be used in other domains. You can add a few attributes onto these goals. We want it to be very easy to pick up and use so that there's a pretty short ramp-up time, which means that people have to be somewhat familiar with the syntax and the semantics of how you use it. Simplicity has to be one of the primary attributes. We want it to be good for use in systems usage like Go is, as well as blockchain usage, so something that's more general purpose. But the special power is that we want to build formal verification in at compile time so that you find these bugs before you actually bake them into the blockchain. So if you know anything about compilers and interpreters, this will be old hat, but basically, we think of an interpreter as being something that runs from source. It's kind of a lot of dynamic stuff happening. We think of a compiler as something that runs from code. You generate code and then you run from that code. So you're actually creating binary. And then we have this kind of in-between thing, which is it's compiling to a bytecode. So you have this intermediate language, which is a bytecode language, and you run from that. So it's part compiler and part interpreter. And then you have this other weird thing on the end, which is a transpiler, which is going from source to source. So here you start with one high-level language and you essentially transpile into another high-level language, and then you compile that language. And there's some examples of all these. Clojure is a transpiler. Go, C++ are true compilers. Java and C# are bytecode interpreters. Ruby, Python, JS are all interpreters that run from source. So our journey, we started actually with a bytecode interpreter. So we created a compiler that would compile to bytecode, and then we would interpret that bytecode. And the reason behind this is we thought, okay, this thing has to live in a VM, so we need control over that VM. So we really do want control over the bytecode and how it executes. So we started out the journey by building a simple bytecode interpreter. We compiled something that started from a Go grammar. A parser generator is something that kind of gives you a leg up on creating compilers and interpreters because it does the parsing for you. It's a tool basically for making something that knows how to parse your source language and create an abstract syntax tree from that you can then work on to generate code or interpret or whatever you want to do with it. So we started with that and with Antler, and I'll show a little bit of what Antler looks like in a little bit. That was version 1, and we got pretty far into that first phase of building our bytecode interpreter. We had definitely compiling, fairly sophisticated Go and extended Go, and then interpreting in a bytecode. But we kept running into issues of not quite perfect. So Go has its own built-in parser, and mimicking that exactly and being 100% compliant turns out to be pretty difficult. So we kept running into more and more issues of just the overhead of creating a full language from scratch. So, okay, we decided, okay, let's go to a transpiler. Let's start from our version of extended Go and then compile to Go. And then we used Antler again for processing that, but same issues. And also one of the things we figured out along the way was that Go really has some very nice type checking tools and parsing tools and AST manipulation tools built right into it. So we decided phase 3, where we're at now, where we're just extending the Go compiler itself to make our tool. Here's just a quick example of what phase 1 looked like when we generated our own bytecode. So here you see a source example there on the left. It's just basically a hello world example. We compile that into Antler's version of the AST. And then from that, we compile into our own bytecode, and then we even saved a binary. So you can see a binary printout of it over there too. So we did have stuff working fairly well. But again, the overhead of maintaining that and keeping it up to date and compliant is just too much. And it's kind of a waste of time. And so segue to here. So why use Go? Why do a transpiler at all? Well, doing a transpiler and using Go allows us to focus on the missing parts, not the base language. We don't have to reinvent Go. We don't have to create all the tools and the ecosystem that are already there. So we get to leverage 13 years of development of the Go language, which is huge. And there are thousands of people and probably hundreds of thousands of man hours going into that. And we can't really compete with that. So we're going to use it. So we build on top of a popular platform. Go is pretty popular. Probably things like Python and Java are more popular, but it's pretty far up there in terms of popularity and use, and it's actually gaining ground year over year. There is a very nice ecosystem and tools package that already exists for Go, including great documentation. So that definitely helps us a lot. We're also building Silvermint itself in Go. So by using Go for Symmetry, we get to leverage the same base language that we use for both, which means that all of our developers become fluent in that base language, and they can help out and we can move around and accomplish more. Go is in the imperative language C family of programming syntax, and that's great because many programmers are familiar with that imperative language style and the C family of syntax in particular. So by going with something in that family, we get to leverage a lot of familiarity. So for somebody who sees this out of the gates, the first thing they're going to say is they've never seen Go before. They'll say, okay, that looks pretty much like a C program or something similar. And if they've seen Go before, they'll say Symmetry looks pretty much like Go with some extensions, which is what it is. So we get to leverage all that goodwill and knowledge that are already there. The other thing that we like is that Go itself is very fast on the compile, very fast on execution. It's a simple language, statically typed, memory safe. So it's just a great base to build on for us. Okay, so you saw in the journey that we started with Antler and then we moved over to Go instead. Why did we do that? Well, the Antler Go grammar, as I mentioned, has a very nice grammar for Go, but it's an example and it's not really maintained. And so it's not 100% compatible with Go. In fact, I think the current version doesn't even support generics, I believe, of their example. And there are no type system tools. There's no kind of nice tool infrastructure around that. It's just the parser generator. That's all you get. On the flip side, the Go compiler and tools are written in Go. So if you know Go, then all the tools and the compiler itself are written in Go. So you're automatically ramped up on that. It also has a very nice sane architecture. If you've been to college and had a compiler class, you're familiar with recursive descent compilers, and that basically is the Go compiler architecture. So it's a nice, comfortable, sane architecture for us to build in, and it's definitely huge. It's a very large compiler, so it'll take a while to understand the full extent of it, but it's not overly difficult. Go, as I mentioned, also has great documentation, so that helps us a lot. And not only the formal documentation that you can see on the websites, but also the code itself is very nicely commented and documented. In addition to just the compiler, there are also other tools that you can use. For instance, there's this thing called the AST util, which is really good at rewriting the AST. So they're building tools and infrastructure around Go, the compiler itself. Similarly, there's the Go vet tool, which is kind of an analysis tool. So stuff like that. So the only issue for us is that Go only understands Go. So if we extend the language by adding new syntax and semantics, Go doesn't know what to do with those. And in fact, it'll crash. So, so what we do is this. So over on the left, you can see here's how we develop it. We take the standard Go that's just right out there on GitHub. We fork that, and then we add to it so that it understands our language extensions. And I'll show you kind of some of the places where we have to extend it. But then when we have our own version of Go, which understands these new language extensions, then we can use that to build our Symmetry transpiler, because now it understands this extended Go language. So we build our Symmetry transpiler, and then people, you can see on the right-hand side, people will use that by taking a .sim file, which again is Go with some embellishments, and then they compile that using our Symmetry transpiler, which compiles from Symmetry, does the analysis, finds any errors in it, and then produces standard Go. And then you can run that standard Go through a standard Go compiler. So the end user never has to have our version of extended Symmetry Go. All they need is the Symmetry transpiler, which we can provide. If they want to, of course, it's all open source. They can look at what we do in the Symmetry transpiler, Symmetry Go toolset, or anything else, but they don't have to. So it simplifies what the customer has to do. So at a high level, what does a compiler look like? This is very, very simplified, but you start with that source.go, which is just your high-level language, and then you scan it. And scanning is really taking that source code in your .go file and breaking it up into recognizable little chunks, tokens. And a token might be a keyword, it might be an identifier, it might be a literal like, to, or a floating point number or whatever. But it breaks it up into tokens. So I lost. Let me see. I lost my Zoom file. Are we still on? Did somebody say something?
I can hear you, Eric.
Okay, good.
Yeah, I can too. Sorry.
Yeah, no worries. I just lost it, somehow booked out on me, but I'll keep trudging on. Okay, so so we have tokens, and then we take those tokens, which are these little chunks of language, and then we have to understand them. So we've essentially scanned them or tokenized them. Now we want to scan them to figure out how they fit together to create bigger constructs. And an example is that a token might be the for keyword, but a language construct might be the for next entire construct, which holds the conditional and how you're going to increment it, and the block that contains all the code that you're going to do inside of that for loop. So those are all part of the bigger construct the parse file is dealing with. So parse file now creates the AST, and the AST is the abstract syntax tree. So that's kind of it really is that. It's taking that language and those tokens and parsing it into these language constructs and putting them in a tree format that it understands. And it's really easy to work around that tree and find things and work on them and analyze it. So that's where we and the compiler do most of our work. So the compiler takes that AST and it does some type checking on it. It does some analysis, some optimization, and ultimately it does some code generation and then links it all together and creates your executable. So that's high level what's going on. We really only work down to the AST level and also in check, which is the type checker. So that's mostly where we do our stuff. And then we rewrite that AST, we change it a little bit, rewrite it, analyze it, and then we stick that AST back, and Go doesn't know that anything's happened. It just sees normal AST. There's a few references on the left, and there will be some more at the end too. So we'll come into some of those. So what does the AST look like? And I apologize in advance for the microtext. We can probably zoom in on that a little bit. But basically, when you take something like this little program on the left here, which is, again, a little hello world with the 1+2 on it, and you run it through the scanner and the parser and then create the AST, you can actually look at that AST with a little function called AST print. And here's what it will look like. So I'm going to zoom in that, and I'll ask, can anybody see this now? Yes or no?
Yeah, I can see it.
Okay, good. Okay, so here you see at the very, very top, we have the AST file. So we basically give it the file and say, print out this AST file. And you can see here's the package statement. You can see that the package name is main. And then you see some declarations. This is a declaration list, which is at the file level. And let's see, what does it got? It's saying that it imports FMT. So that's what this part is saying. And then we have the function declaration for main. So here you see at line 23, that's what's this guy right here. So you're seeing this function declaration over here. That's at line 23. And you'll see here's the name main, which is an AST.object with that name. And then there's a function type, which is, it's a construct telling you what kind of function this is. And it's got a list of parameters or arguments, and there aren't any, so there's just an open and close. And then we get into the body of it, which is this little bracket right here. So that's the block statement that's happening right here at line 40. And then we can go into that, and we see that, let's see what next. Next is fmt.println. So it's breaking that apart into the selector, which is the FMT, and the identifier, which is the println, which is a call expression. So you can see right here at line 44, that's a call expression. So it's calling that function. And then again, it has the lparen because this is a set of stuff inside of that function. So here you have that open paren right there. And then you see a bunch of arguments here. And inside the arguments, there is a string, which is hello. And then there's this other thing, which is a binary expression. And you see that here, which is 1+2. And that binary expression has an integer, which is kind int with a value of 1. And then it has this operand plus, which is the addition. And then it has this other thing called the integer value of 2. So it adds those things together, and those are part of the arguments that go into that FMT println. So you can see that the AST is got a lot of information into it about what types of things are there, how many of them, what kinds, and how they kind of flow up into this AST structure. So that's what we do our work on. Okay, so now I want to pop out and show some of this stuff in the website. So I'm going to unshare and go somewhere else. So now I want to go. Shoot, they're all separate. Okay, well, we're going to go full screen then. Okay, is that legible? Somewhat?
How much of it do we have to read?
Not too much, no.
Okay.
I'll pop it up a little bit.
Thank you.
Okay, so this is the Antler site. So if you come out here, this is Antler, which is another tool for language recognition. So it's a parser generator. And there are a ton of parser generators. So if you go out to Google, Wikipedia on parser generators, there's a ton of them. And this is just one. It's a modern one, easy to use. There are a bunch of grammars for Antler. So here you see all kinds of languages that they have example grammars for. Tons and tons. Here's C right there. And Go should be right in here somewhere. Right there, Golang. So if we pop into there, and we pop into Go, and we pop into the Go parser.g4. So here is the G4, which is their input language for the parser generator. So you can see this is basically the definition of their Go grammar. So that was all phase 1 and 2 stuff. Now, phase 3, we went to the Go programming language itself, and you can see that's out here at github.com, Golang Go. So you can download this and you can compile it yourself and create your own version of the compiler, and that's exactly what we're doing. I talked about all the good documentation there is. So for instance, here's an example of documentation that exists for the parser. You can see this is all in the Discover Packages standard library for the Go parser. Here's the AST. And again, you can see some of those things, structures that we talked about, different types of structures that the AST and the parser use. Here's that other little utility I told you about, which is actually in a different repo. It's in Golang X tools, but here's a AST util, which is just a utility for rewriting the AST. So that gives you a nicer ability to change the underlying AST. Here's more good documentation. If you go into Golang examples, here's a whole bunch of examples and some great documentation on the type checking tools and how you do type checking and organization. It's fascinating stuff in here, especially for people who like languages. The Go programming language specification itself, which is in Go Dev Ref Spec, also has a ton of information about types and the basic structure of the language, and even talks a little bit about some of the structure of the AST. So lots of good stuff here. Okay, let's see, where was I? So what did we do? How did we change this thing? Is that legible?
Yes.
Okay. So we made some language extensions, and these are the things that we added to the base language of Go. And they kind of fall into 3 different categories here. The first thing we added was a set of asserts, or a assert, that uses the Z3 solver to verify assertions. So Z3 is SMT solver, and basically what it does is allows you to say some, to point some statements at it, and it will parse those statements, and then you can make some assertions about things you believe to be true about those statements. And it will tell you whether that statement or those statements are true or false. So it allows you to verify some assertions that you're making about the language. And I'll give an example of that in a little bit. We use another extension, which we call layers. And the reason we use this is to restrict portions of the code to subsets of language features. So for instance, we have one called core, and core is a very safe subset of the language features, which you cannot change any state in it, which means that it functions a lot like functional programming in that you can pass things in, do some work on them, and pass out new structures, but you cannot have any side effects. We also care a lot about randomness. So, one thing in Go that creates randomness is just how you iterate over a map structure. So if you iterate over a map, it's not guaranteed to iterate the same way twice. It's guaranteed to hit every map element, but it may actually hit them in a different order. So that creates randomness, and that's something we want to avoid. So these are things that we want to restrict in that core layer, so that you're absolutely sure that you have a secure core layer. So this allows us at a high level to make it much easier to verify our code, to reason about it, and most importantly, to reduce side effects. Another construct we added was algebraic data types, which again will be familiar to mathematics and computer science people, but basically allows you to control, to create some private interfaces so you can control your type safety. So you can only create side effects by calling known methods on that, and you can only create new structures if they are of a specific ADT. There's an interesting method that's called object capability, or the OCAPS model support, which I'll talk about that a little bit, but this basically allows you, it's all kind of the science and the mathematics behind secure OCAPS model. We're also going to provide some map and reduce methods on these ADTs to make them easier to work with. So here's a couple examples of how that works. So here's an assert. So for instance, if we look at this, this is just a function, Go function. It's called add1. And basically it's taking A and B int, which are both int16s, and it's popping out 2 int16s on the return. So we call C equal to A plus 1, and we call D equal to B plus 1, and then we do an assert that C is going to be bigger than A and D is going to be bigger than B, which on the face of it seems to make sense because we're adding 1 to each of those, and we return C and D. So what we do is we take that thing, we send it off to Z3, and you can see here that we're using something called SMTlib as a format to describe how we're breaking apart these statements and turning them into things that are compatible with Z3. So here we take the C plus 1, and we're saying, first of all, we define what A, B, C are. They are bit vectors of 16-bit length. And then we're asserting that C is equal to an add of A plus, in this case, X, which is a 16-bit 1. And we're saying that D is equal to an add of B plus a 16-bit 1. So we assert those two things. And then we assert, we do a negative assert here, but basically we're asserting that these things hold true, that C is always going to be bigger than A and D is always going to be bigger than B. And then we run this check stat, which is saying, check to see if this is satisfiable, and then in return also get the model for us if it isn't. We run that through, and then Z3 spits back an answer that says it's sat, or in this case, since it's negative, it means it's unsatisfied. And the example is right here, which is saying that the thing that we forgot about when we set this up is it's true that C is generally bigger than A and D is generally bigger than B, but this is a signed 16-bit integer. So half of it is negative and half of it is positive. And at that halfway point, it flips and it's not true anymore. So once your B gets to basically, I believe it's 32767, then your A is also 32766, or when your A is also 32767, then your D and your C and D are going to be one bigger, which are going to be 8000 hex. And at that point, they're negative, so they're not actually bigger. So this is the model that it gives you back. So it's kind of cool that it finds these things for you. Here's an example of layers. So here, in fact, you can see the syntax of it. So we have this generally standard Go, but in this case, we're going to add a layer mark in front of the function mySum. And we're saying that this function mySum is core. So that means it has to hold, first of all, to all the restraints that we put on a thing that's labeled core. In this case, it does not, because one of the things that we say about core is that it has no side effects. In other words, it cannot produce any side effect to an underlying data structure that's passed in. So here you see that this would make sense on maybe at a naive level. We pass in A and B as integers, and then A is equal to, or we add on B to A, and then we return that as the sum. So it seems to make sense. However, if we look at actually what runs, what happens here is we pass in A and B, and initially A and B are 3 and 4, as you can see here, and the sum is indeed 7, as it should be, but because we added it to A, the side effect is that we added it to A. So now we've changed A from 3 to 7, the sum. So that's not good. We've created a bug. So, but of course, we'll find that bug because we labeled it as core. We didn't want any side effects. And so when we run it through the Symmetry transpiler, it does the analysis. It sees that right here, when we do A plus equals B, we're actually doing a sign. And assign once you defined a value is not allowed in core. So you get this error down here that says you've got an assignment in core right there. Here's another example, a little more detailed. This one has to do with interfaces, and interfaces are pretty central to Go. Here we define an interface called dog, and we say that both of the interface methods are marked as type core. And so we have a size and a color. And then we define these two things which implement the interface. One is a poodle. So we have a poodle here. He has an extra thing called a name, but he does observe the dog interface by implementing a size and a color of type int and string, as you would think. And we label them both as core, so poodle looks good. We have this other thing called terrier, which is also, we would like to be a dog. And we implement his interfaces as well. And they're both also of type int and type string. So they look good on the face of it. However, if we label this as core, the first thing that happened is once we run this through Symmetry, this would return an error because we're setting t.barks equal true. So in other words, we're doing assignment inside of core, which is not allowed. We're changing state. So, okay, we say, fine, okay, it's not core. Maybe it's stateful because stateful allows us to change state. So now we assign it to stateful. Well, it turns out that fails as well, but that fails in a different spot. That will fail down here where we, right here, assign your dog to be a terrier because we defined your dog as a dog, which means it has to observe these two interfaces of size and color of layer types core. And that means that the thing we assign it, which in this case is a poodle literal, this case, which in this case is a terrier literal, also has to observe or implement those interfaces. But terrier, when it does the analysis, finds out that terrier has core and stateful. So the interface implementations don't match, and you get the error. And here's the error. So that's how use of layers helps you to write better code that's bug-free. And finally, here's the ADT. So here we start with this new construct that we created called a sum. We have a little prefix on it called sim underbar. So it's a sim underbar sum. And we define it as a tree. This one has a generic type of x any. And inside we define a type of node and another type of leaf. So when we run that through the transpiler, it creates new code, which it breaks apart the tree type into be an interface, and it's got a private method on it. In this case, it's is with a long number ending in 5.3, and everything that it creates inside of that sum also holds that interface. So you can see that both the node and the leaf also create that interface as well. But again, they're private, so you have to have a constructor to create things of this data type. So that's how that one is made safe. So now I want to show one more thing here. Coming back to Go itself. So again, coming back to github.com, if you go to the Go language and grab this compiler and download it and compile it yourself, you'll find out that it actually does compile pretty easily. I talked about some stuff inside of this thing, the scanner. So here you see scanner.go, and this is inside of source go scanner.go. So if we go down, I think it was at the bottom. Yeah, so there's scanner.scan, which is the main scanner for the Go compiler. So this is the thing that is creating the tokens that I talked about. We don't do a whole lot of work in scanner. We don't have to because we create new tokens, but we don't actually change the scanner itself. So inside of token.go, here's where we define the actual tokens itself. And here you can see we did define some new tokens. If we go down to right here, line 134, you can see that we define a few new tokens, the assert token, the sum, and the layer token. And if we come down here, you see where they're defined. So here we have sim prefix, which is that sim underbar plus assert, sim prefix plus sum, or sim prefix plus layer. So those are just new tokens that we added that it now will look for as it parses. Interface.go, which is in source Go parser interface.go, is the place where the parse is kicked off in parse file. We don't really change that very much, but the guts of that are actually contained in parser.go. So here's where we have parser.go, which is parse file. So parse file is the thing that that it's actually calling to do the work. And then parse file, again, it's recursive descent parser. So it's calling other things to figure out how it's parsing that source code in the set of tokens. So we have to change this. So you'll see, for instance, where is that? Yeah, right. Some spec. So here we go. So that sum construct that I showed you earlier, here's where we parse that. And that will make more sense actually when we look at the AST. So we have to change AST.go too, which is where we define new AST structures that we need to support our new version of the AST. So here, for instance, in AST.go, you can see here's sum spec at line 934. So it has, here's the sum token, here's the identifier for the sum spec itself. Here's the list of types that it holds. Here's the that's the type params. Here's the left brace. Here's the list of types that it holds. Here's the right brace, and here's the type. So that is the AST for the AST structure for sum spec. And then here's where we parse it at line 2771 in parser.go. You can see that here we're parsing that identifier. Let's see, we've got the left brace right here, and we've got the type right here, and we've got the set of, or the list of identifiers, or sorry, the list of types right here, and then the right brace, and then if there's any comments. So here's how we parse it. We pull it in, and again, here's how, this is kind of how we're extending Go. Few other things to look at in, I talked about type checking. So once we've created that AST, we also sometimes need to look at what are the types of those things, those identifiers that were created. So API.go, which is in source Go types, API.go is where that's kicked off in a function called check. And let's see, what else? Yeah, the only other thing to know is that every identifier is an object, so you might have to extend source Go types object.go as well. So I think that's about all I had to say.
Cool. So following the format, I will leave it open for questions for the next few minutes. I'm going to kind of repeat what I said on the validator call. Eric is really good at, answering questions at all different levels. So feel free to ask anything from super technical to something that's not so technical. That's kind of what the whole point of this is to open this up for like an open forum and just have debates and talks about, what we've been building and how we can make it better for the community. So with that in mind, I'll leave it open for a few minutes for some questions to come in.
Yeah, I had a question about like the AST file. It's kind of a more general programming question, not necessarily anything specific to Go. I was interested in knowing, thinking about coding and how they talk about how some languages are more high level, or something like C is more close to the metal. How does that affect the AST file? Like something like Python, does it have a much more bloated AST file?
I think that yes, the AST does reflect the complexity of the underlying language. And so I think the more simple your language, the more simple your AST will be. So Go is actually one of the more simple syntaxes, believe it or not. I would hate to parse JavaScript, but yeah, I think it would reflect the complexity of the underlying language. You mentioned C. C is also a very simple, structure language, so even more so than Go. So I think you'd find a much simpler AST inside of C. mean, if you think about C, C doesn't have maps, and man, it just doesn't have a lot of, well, it doesn't have runes, you know, doesn't have Unicode. There's a lot of stuff missing from C that Go is dealing with.
Eric, there was a good question. For those of you who don't know, yesterday we actually were part of the Gophers of Utah. Like, we went to their meeting and had our CTO Mike Stay actually speak on stage. And a good question that someone asked was, why did we choose Z3? And did you have any input in that, Eric?
I'm not as well acquainted with Z3 as, for instance, Philip is, but I would say that it is one of the most bulletproof and popular SMT solvers out there, and I think it's got good documentation. So I don't think, you know, we've excluded ourselves from using some other solver, but that one fits the bill, and it seems to be fairly well tested. We talked to a few researchers yesterday, and one of the things that they were talking about is that it does run into issues with scalability. So if you're throwing a bunch of SMT lib at it, it might just time out and not be able to handle it. So we are going to have to think about how we reduce what we send to it so that it can handle it all.
I mean, I can ask you questions all day. Why is it important to have formal verification within a smart contracting language? I think you kind of hinted on it in the beginning, but I think a lot of people within this actual meeting, and maybe some of the people that are going to watch this video later, might not have an idea of the importance of that. Like, why is it important that we're building Symmetry, and like, what's the major problem we're trying to solve?
Yeah, again, the major problem we're trying to solve is to reduce bugs. And there are certainly existing standard ways of doing that. You know, one way is just testing. So you can test your code, and the more you test it, you know, presumably the better it gets. You can run tools like profilers and code coverage to see, you know, how well you think you're testing it. But in the end, testing only tells you that there are bugs. It doesn't tell you that there are not bugs. So you can't prove that there are 0 bugs, or how, you know, exactly quantify how stable or how secure or how safe your function is. And I think that's what formal verification gives you, is the ability to actually formalize that and theoretically prove that you've done the right thing. You don't have to try kind of a hit and miss test approach to find problems with it. You can actually prove through the code itself that it is correct.
I'm going to leave it open for a couple more minutes, and then if we don't have any more questions, we can close off. So I'll leave it, like I said, maybe a minute or two longer. See if anyone has anything to say.
Hey, Eric, outside of blockchain and smart contracts, I'm just curious, as you've had your head in this space for quite some time, are there problems that you have encountered as a developer before, or that you could imagine developers encountering, that would benefit from these types of tools that are not blockchain related?
Yeah, for sure. And I think, you know, again, having bugs is not specific to blockchain. I think there is a pain point that it's more painful in blockchain and potentially more expensive, but it still costs, you know, trillions of dollars in problems for people every year for having bugs in code. Outside of blockchain, they might be a little bit easier to fix, but that doesn't mean that they're not costing you a lot of aggravation and dollars and maintenance. So
Right. Yeah, no, that makes a lot of sense. And also, you know, again, because you've had your head here, when you think about if you were using these tools to mitigate that risk outside of blockchain projects, can you talk a little bit about what that overhead cost might add for your work as a developer?
Yeah, I mean, right now, testing, you might think testing itself is an overhead. So you write some code and you write a test for that code to prove to yourself that you think it's working. And then you might, write more code to prove that it's broken or not broken in other areas. And so you kind of continue to write tests against your code, and that makes it better and better. So that is a bit of overhead that you're doing for the sake of making better code. And this is just another tool to do the same thing. So instead of writing tests against your code, you'll write assertions against your code. You'll say that here's what I believe is happening in front of my function. Here's what I believe is happening within my function. And here's what I believe is happening when my function returns. And you can assert against those things and formally prove whether or not they're true. So it's another tool to use. I would say one difference is that, as I said before, testing is kind of a scattershot approach. In fact, there's a type of testing called fuzz testing, which is just really is shotgun, where you're trying a whole bunch of random things to try to find anything that breaks. It's like the proverbial monkey on keyboards approach. And you're just kind of hoping that through that big shotgun blast of randomness that you'll find some bugs. And a solver is a little different. It's saying that here's how my code works, and here's what I believe is true about it, and tell me whether or not through analysis whether you believe that's true. And then it goes off and chugs away and looks at your code and does the S&T solving and gives you either yes it's true or no it isn't true, and here's why. So that's kind of cool.
Yeah.
It's in the new phases. I mean, this is a new thing. I would say that use of SMT solving for code correctness we're on the very beginning of that, and there are other languages that are beginning to use it as well. I think Microsoft has one called Daphne, and so it is starting. I think it's in the very beginning part of being a general purpose tool. So it's not quite there yet. But I think this is a great application for it because, again, the stakes are so high if it's wrong.
Yeah, that makes a lot of sense. Thank you. And then last one, I know obviously no one on this call right now, and certainly no one that's listening would ever be a developer that doesn't do any testing. And yet we know that those people exist. What advice would you give to somebody maybe who doesn't typically do a lot of testing? Maybe they just kind of poke at things. If they were going to pick up tools like this to do formal verification, what advice would you give them just in terms of like adopting that as part of their process?
Yeah, I mean, that's kind of baked into the TDD mindset, which is the test-driven development. And the idea there is that you write some tests and then you write code that satisfies those tests. So it's kind of a reversal of testing afterwards. But I would also say Go has some great test tools built into it. I mean, there's actually a nice little test harness and functionality built right into Go, and it makes Go a really nice way to develop tests. I would say that everything you can do to make it easier for people to test or verify their code makes them more likely to use it. And so just like Go made it a little bit easier to test your code by building in some nice tools and constructs to make testing easier, if we do a really good job with Symmetry of integrating Z3 into it, that will also make it easier. You can think about, it's pretty easy to say, I believe these few statements are true about my code. I don't have to write anything inside the code. It's just going to analyze the body of the code, and then I'm going to say some things that I believe are true, and it's going to tell me whether or not they are true. That's pretty easy. I mean, it's probably easier than writing tests.
That's the t-shirt. Thanks, Eric.
Yeah, easier than testing.
Okay, it's 7:52. We can end it here. I'm just going to add, if you weren't able to attend last night, we're also going to be, we've already recorded that video. We're going to be pushing out to both Discord, our LinkedIn, and a few other mediums, just in case you want to watch it. we're also going to do the same thing with this video. We're going to be pushing out to Discord. Next week, if you have any questions or any suggestions, make sure to reach us in our Discord. If you haven't already done so, please join, just so that way we can make sure that we have an open communication. I will try my absolute best to answer any questions you may have regarding whether it's development on Symmetry or whether it is on the side of the validators. So if you have any questions, shoot them to me in there. My handle in there is Nikki Pyro, so just make sure to @ me in there. And without further ado, I think we're going to end there. So everyone, thank you. Thank you, Eric, for having this with us. And thank you, everyone, for attending.
Thanks,
Thank you.
Nikki. Thanks so much.